Okay, good morning everyone and welcome to the 2013 Royal Tyrrell Museum Speaker Series. Today, the Royal Tyrrell Museum and its cooperating society are proud to present Dr. Cory Redman. Cory is a postdoctoral fellow here at the Royal Tyrrell Museum. Cory is originally from Wisconsin, but he grew up in Montana and Idaho. He obtained his bachelor's degree in geology and zoology from the University of Wyoming, and after obtaining his degree, Cory moved to Southern California to pursue a master's degree in the Department of Biology at San Diego State University, where he studied the paleoecology and taphonomy of the Upper Cretaceous Bisecti Formation of Uzbekistan. Subsequently, Cory moved to Texas to pursue his PhD in geology at the Texas A&M University, where he studied the use of vertebrates to understand the factors that influence terrestrial ecosystem structure. After completing his PhD, Cory obtained an NSF postdoctoral fellowship to come study the latest Cretaceous and earliest Paleocene ecosystems of Alberta. Cory's research interests focus on quantitative evolutionary paleoecology, or in layman's terms, to quantify how terrestrial ecosystems have changed through time and with respect to environmental changes. Over the years, he has conducted fieldwork in Alberta, the US, Mexico, England, and Uzbekistan. I should add Saskatchewan too. Today, Cory will review how ancient ecosystems of Alberta fared during a time of major sea level and climate changes. So without further delay, I present you Dr. Cory Redman.
Thanks, Francois. Can you guys hear me? All right. So, as Francois mentioned, the title of my talk is Revisiting the Paleoecology of the Belly River Group of Southern Alberta. I included the term revisiting because the paleoecology of this particular rock group has actually been well studied over probably the last 40 years. But my particular research is kind of taking another small step forward, and that's why I included examining regional changes in diversity. The diversity of this rock group has really not been statistically quantified with any robustness, despite how well the fauna of the Belly River has been studied. So before I continue, though, I need to acknowledge my co-authors. This was part of my dissertation research at Texas A&M University, so I need to acknowledge the support and help from my PhD advisor, Tom Olszewski, and also Don Brinkman. Don, is your middle initial really B? I didn't know if Gardner was pulling one on me or not, so just thought I'd ask. But Don was actually a big help in making this research happen, providing me with additional data sets that were unpublished, answering my numerous questions, and helping me learn to identify microvertebrate fossils. So, how does diversity change through the Belly River Group? Most of you guys already know this, but Belly River Group is about 77 million years old, which is a part of Earth's history we call the Cretaceous. Specifically, it is part of the late Cretaceous that we call the Campanian. But for the purpose of this study, I'm only going to be looking at about 3 million years of the Campanian, which represents kind of the span of the fossils that I'm looking at in the Belly River Group. So the Belly River Group basically ranges in age from 80 to 75 million years ago. It's composed of the foremost, the Oldman, and the Dinosaur Park formations. The very upper part of the Dinosaur Park, the upper 10 to 20 meters, is pretty distinct lithologically and environmentally, and it's broken out and called the Lithbridge Coal Zone. For the purposes of this study, all the fossils I'm working with basically come from the very upper part of the foremost up through the top of the Dinosaur Park formation, stopping at the fully marine bear paw. Okay, what did North America look like 77 million years ago during the Campanian? Well, sea level was much higher, resulting in a shallow sea connecting the Gulf of Mexico to the Arctic Ocean. There was basically this giant shallow seaway. The red star basically denotes where we are in southern Alberta. And sea level was not static during this time, at least during the deposition of the Belly River Group. It actually fluctuated. So the Belly River Group is bound above and below by fully marine sediments. And then the foremost, you actually see a relatively a relative drop in sea level, which we refer to as regressive paralletic sediments. This just means that you have kind of non-marine, marine sediments interfingering one another as we see a relative drop in sea level during the deposition of the foremost. The Old Man Formation is non-marine, and this represents the kind of maximum drop in sea level during the deposition of the Belly River Group. Once we hit the Dinosaur Park Formation, sea level is beginning to rise back up, even though the majority of the Dinosaur Park is non-marine, until you hit the Lethbridge Coal Zone, in which you have transgressive paralitic sediments, so you get that interfingering with the rise of sea level until you have the fully marine sediments represented by the Bear Paw Formation. Just to show you some visual images, this is kind of what southern Alberta looked like during the deposition of the Oldman. Instead of kind of being a dry prairie, it was more of a wet coastal plain setting, very extensive coastal plain. Coastal plain just basically refers to a large area in which it's bound on one side by sea and the other side by kind of a high province or mountains. It's a very lowland area. When we move to the Dinosaur Park, we see kind of a change in the river systems from basic kind of seasonally wet, dry, low sinuosity, greater sinuosity meandering systems, usually a little wetter. And then when we hit kind of the Bear Paw Lethbridge coal zone transition, it's basically much greater influence, tidal influence in the rocks that we see. And this is just kind of a depiction of kind of what the Bear Paw coastline would look at once you had the flooding. All right, so for the purposes of this study, we're looking at diversity through time using what are called microvertebrate fossils or microsites. And these are fossils, these are basically fossil sites that produce an abundance of small disarticulated skeletal elements. By abundance, we usually mean greater than 150 identifiable specimens. And small, they range in anywhere from 1 millimeter to 10 millimeters. The diameter of this bowl is roughly 12 centimeters. And the idea is we use microvertebrates to kind of reconstruct the ecosystem of the landscape. These are extremely powerful fossils because not only can we capture the very large taxa, famous dinosaurs, but we can also capture a lot of the smaller taxa that are generally more abundant on a landscape. This particular reconstruction is not of the Belly River group. It's actually of another Campanian age deposit called the Mesa Verde, which is actually found in Wyoming. But a lot of the taxa that you see here, you also find in the Belly River group. For those of you that aren't aware of how we go about collecting these small microvertebrate fossils, it can be a labor-intensive process like anything in paleontology, but first thing you do is you prospect, looking for basically fossils that are weathering out on the surface. Commonly you find small fossils weathering out or concentrated on a flat. Then what you proceed to do is identify the fossil producing horizon in which those fossils are weathering out of. Sometimes it can be this whole section of exposed outcrop, but a lot of times it's actually an individual horizon, a very thin horizon. Sometimes it's very easy to identify these horizons. Sometimes it's impossible. Once you have identified the horizon where the microvertebrate fossils are coming out from, you literally bulk sample. You basically sample that horizon, bag it up, and haul it out. If you're lucky, it's right next to a road. This rarely happens. Usually, it's in something like this. So you basically backpack it out. Once we've backpacked the bulk matrix out, we basically screen wash it, dump it in screen boxes to basically try to reduce the bulk sample as much as possible to concentrate the fossil material. This is commonly done in water, but you can also do it in various different types of diluted acids. Then we go about picking the concentrated matrix, pulling out all the small microvertebrate fossils, and then identifying them. For the purpose of this study, to look at regional changes in diversity, I combined both data sets that have been previously published with additional sites, and there are about 10 fossil sites that are actually recollected to increase the sample size. This came from two main areas of southern Alberta, Dinosaur Provincial Park and the area near the small town of 1-4. After kind of updating, rationalizing, collating all the various faunal lists and abundance counts from all the publications and the new material collected, our data set basically composes of 92 taxa from 66 microsites. So it's a really pretty good sized sample. So we need to talk about basically how does the geology change between Dinosaur Provincial Park and 1-4. So you've seen various parts of this diagram before. This first column just shows changes in relative sea level. Again, sea level is lowest in the Ullmann, and you have these interfingering marine, non-marine sediments in the base of the foremost and the Lethbridge coal zone. The two dark columns show the radiometric dates that we have based on tuffs for the two locations, Dinosaur Provincial Park to the north, 1-4 to the south, and then basically the list of formations or rocks exposed at both of those locations. The meters actually refer to the exposed outcrop. This does not include total thicknesses of the section of the rock units. As you can see, Dinosaur Provincial Park, we have microsites from the upper 20 meters of the Ullmann throughout the entire 70 meters of Dinosaur Park, with Lethbridge coal zone about 10 meters at the very top, capped by the bear paw. If we go to 1-4, the formations actually change thicknesses. So the Ullmann is much, much thicker in 1-4 than it is at Dinosaur Provincial Park. Dinosaur Provincial Park, the Ullmann is about 40 meters thick, but only the top 20 is exposed. We're only looking at microsites from the upper 20 meters of the foremost, even though it's much thicker. And then Dinosaur Park actually gets much thinner in the 1-4 opposed to Dinosaur Provincial Park. And the Lethbridge coal zone, which is the LCZ, is actually quite a bit thicker. So not only does the thicknesses of the lithostratigraphic units change, but as you move from north to south, the age of the sediments get younger. 77 million years is roughly at the Dinosaur Park Ullmann contact in Dinosaur Provincial Park. In 1-4, 77, you're basically in the middle of the Ullmann. If you look, the Lethbridge coal zone is roughly 75.5 million years, but at 75.5, you already have the Bear Paw Sea in Dinosaur Provincial Park. So you need to make sure and keep this in mind. I'll be coming back to this diagram many times, so they get plenty of refreshers. This is just to show the distribution of our microsites through the different stratigraphic sections. I don't expect you to memorize the relative position of any of these sites. I just want you to show we have basically relatively good sampling throughout the entire section, both at Dinosaur Provincial Park and 1-4. There are a couple sections in 1-4 that are lacking, but for the most part, we have really good uniform sampling microsites throughout the section. Okay. Previous studies of the microvertebrate fauna from these areas identified basically two fossil communities. Now, a community just refers to a group of organisms that co-occur in the same habitat or area and basically interacted with one another. This is a good definition to keep in mind because I'll be using the term community off and on throughout the whole talk. Anyways, previous analysis basically identified two communities, a coastal community, which referred to vertebrates that had a higher abundance in the estuary-dominated areas of the coastal plain. So these are the areas of the coastal plain that had stronger tidal influences, such as the very top of the foremost or the Lethbridge coal zone. And inland communities, which referred to vertebrates that had a higher abundance in river-dominated areas of the coastal plain. So these are taxa that are strictly terrestrial or freshwater restricted versus taxa that were brackish or marine tolerant. Since I'm conducting this study, kind of compiling both previously published data and new data, I needed to update and kind of rationalize all the fauna lists. So we were calling the same taxa the same organism. To make sure that we could still recognize these coastal communities, which had been well documented in the literature, I used a multivariate technique that we call ordination analyses. I don't have enough hands. Ordination analysis is basically just a mathematical technique that graphically summarizes complex relationships by extracting one or a few dominant patterns and mapping those objects in space. So this is just an ordination plot. This is a relatively simple example. It's really easy to read. Objects, in this case sites, that are closer to each other in ordination space are more similar. So in this example, we have 4 fossil sites and we have 4 identified fossil taxa. I just used taxon occurrence data, so the 1 just shows that that fossil is present at that particular site. 0 is it's absent. You can replace the 1s with abundance data, such as counts of identifiable specimens. And as you can see, site 1 is more similar based on its fossils or its taxa than site 2, and therefore they occur closer in ordination space. For the purposes of my study, I'm using taxon abundance data. So I'm replacing these 1s with a number of identifiable skeletal elements that can be assigned to a particular taxon. The reason I keep using the term taxon is because most microvertebrate material is all disarticulated individual skeletal elements, I can't necessarily assign it to a given taxonomic level. I can't assign it to everything to a certain species. Sometimes I can only assign a particular bone element to a genus or a family or a higher level. So I'm just calling them all taxa. I use taxon abundances, 92 taxa from 66 microsites. What makes ordination so powerful is in this simple example, there are over 16 possible axes that can account for the variation that we see in this data set. Now, I don't know about you, but I have a hard time thinking in 16 dimensions, let alone when you increase the size of your matrix from 92 times 66. Ordination is basically looking at the variation in your matrix and axis 1 accounts for that greatest amount of variation. The metric that I used for this study is called non-metric multidimensional scaling, or MNDS. I don't want you to get caught up on this. It's just there's many different ways you can run an ordination analysis, many different metrics. Everybody has their favorite. Mine just happens to be NMDS. The reason I use NMDS is it's considered to be extremely robust with respect to ecological data. Depending on what measurement you use, like all statistical analysis, depends on what assumptions you're making, and you want to make sure not violate those assumptions. Otherwise, the resulting pattern is null. So what we'd expect to see is if we can indeed identify the 2 fossil communities that were previously shown in the published data, coastal versus inland, we'd expect to see coastal communities, those microsites from the upper Lethbridge coal zone and the foremost, grouping closer together in ordination space versus the microsites from the non-marine sediments of the Dinosaur Park and the Oldman Formation grouping closer together. That's what we'd expect. And, well, okay, let me walk you through the diagram. This is the results of the NMDS. So this is just axis 1 versus axis 2. Axis 1 accounts for the maximum amount of variation you see in the data set. Microsites coming from the Lethbridge coal zone and the upper foremost, the estuarine-dominated parts of the Belly River group are labeled in the light blue. The symbol refers to the depositional environment from which the microsite was sampled from. So the diamond is a marine mudstone. There's 3 sites from the upper Lethbridge coal zone in Dinosaur Provincial Park that are fully marine, come from fully marine sediments. Muddy channel fill and sized valleys make up the rest of the Lethbridge coal zone microsites, both at 1,4, and there are 2 non-marine sites in Dinosaur Provincial Park. Shore face deposits are represented by the 2 microsites from the foremost formation. Sandy channel fill by the open circle. This is dominantly where microsites from the Dinosaur Park come from. And then crevasse blaze. A crevasse blaze is just kind of a lobed shape deposit that results when you have a flooding in a river or high energy, which causes the water to kind of break through its overbank deposits. So crevasse blaze are more commonly found in the Oldman, but are also strictly non-marine. So those are the 5 main environments, but we have a couple of kind of unique exceptions. There's one site that's found in a crevasse channel in the Oldman, and there are 2 sites that are kind of fine-grained channel fills that are similar to the mud-filled valleys that we see in the Lethbridge coal zone, but they're unique enough that we kind of just break them out. This includes this site, which is actually an abandoned channel, and then this other one, which we're not entirely sure what the depositional environment is, but it's much finer grained. So, okay, now that I've explained how you look at the figure, it's pretty easy to read. If you look at the microsites that come from the estuary-dominated portion of the coastal plain, you see basically a gradation from having a higher abundance of brackish and marine-tolerant taxa to including more and more rare terrestrial or freshwater restricted taxa. There's quite a bit of variation, but you kind of, these cluster much closer together than they do to the non-marine sites. The non-marine sites actually cluster really tightly together. There's a slight division between location. So the Dinosaur Provincial Park microsites, for the most part, start with the BB, and the microsites from the Lethbridge coal zone start with an L. So you kind of see most of the Dinosaur Provincial Park microsites grouping together, separated from the microsites from the Oldman. While the Dinosaur Park microsites are dominated by sandy channel fills, there are plenty that come from crevasse blaze, and they still group together. This division is basically a reflection of, there are a few taxa that are only found in Dinosaur Provincial Park, and this is also probably a reflection of the sites at 1-4 in the Oldman experience much more seasonal, kind of wet-dry systems, and we're probably on a much better drained coastal plain. If you look at the 2 sites from the upper foremost, which are from the regressive paralytic deposits that enter fingering of marine, non-marine, they kind of fall in between the 2. You would expect them to group closer with the Lethbridge coal zone, but even though they are dominated in abundance by brackish-tolerant taxa, they still have a really high abundance of terrestrial taxa. So they really are kind of an intermediate between the 2. And then there are also kind of 3 exceptions with respect to the non-marine. You have Cretan, you have BB54, and L1108. Those 3 sites, this one is another fine-grained deposit, so its position isn't entirely surprising. But these sites just have a high abundance of 2 taxa, a gar, and a ray, that are basically considered brackish tolerant. And then these 2 sites are non-marine, but they are found in the Lethbridge coal zone as part of the incised valley. Okay. So we can identify both coastal and non-marine sites in our regional scale analysis, which is good. So any modifications that I made to faunal identifications isn't sufficient enough to change the pattern, which is a good sign. But first we need to have before we actually look at diversity of changes in diversity through the Belly River group, we need to have a brief discussion about what is diversity. How do ecologists and paleontologists go about defining diversity? And why is it so important? So diversity is just a measurement of the number of species and their relative abundance in a biological system. We're always interested in diversity and how it changes through time and with a result of environmental perturbations, because it reflects the biological system's state, and as such can provide insight onto the processes acting in and upon the system. You can use many different metrics to measure diversity, but what's really powerful about diversity is you can measure it at different scales. And depending on how diversity is changing at different scales, this can provide insight into what processes are acting on it or causing that change. So you can look at changes in diversity in the grasses across a field just using point samples. You can look at changes in diversity through a forest based on the more dense older forest versus the younger, more open expanded forest. Obviously, it's much larger scale. You can look at diversity across the landscape. How does diversity at a mountaintop compare to the diversity down in a river valley? Or you can even look at it at the scale of the entire Earth or provincial provinces, biogeographical provincials. Probably the most commonly measurement of diversity is what we call richness. A lot of people consider richness and diversity kind of synonymous with one another, but there are differences, and there are pertinent differences. Richness is simply the number of different organisms observed in a collection or sample. Richness is probably the most commonly reported type of diversity in any publication. One of the reasons why is because it's really easy, right? You simply are identifying the specimens that you have in a collection and reporting those identifications. But richness is really not considered a good estimate of diversity of a system because it's extremely biased with respect to sample size, and richness does not reflect the abundance distribution of the taxa within the sample. So if you increase your sample size, you're almost always going to increase the richness that you have. With respect to abundances distribution, just have a quick example here. We have two communities, community 1 and 2. Y-axis is just abundance or richness. X-axis is just identified taxa, in this case A through H. Community 1 has much lower evenness because the abundance distribution between taxa is disproportional. It's basically dominated by an abundance by 2 taxa, opposed to community 2, in which you do have higher abundances of certain taxa, but it's a much more even distribution. If you just report richness, you cannot tell the difference between these two communities, all right? Even though they have much different structure. The other problem is maybe the only reason why community 2 and community 1 have these different distributions of abundance or evenness is because you haven't achieved the same sample size in community 1 as you have in community 2. One of the ways we try to deal with this or overcome this is we use what's called rarefaction. Rarefaction allows us to compare different sizes from one another to determine which one is richer. So basically we're comparing different collection sizes to determine which one is richer. We're trying to account for differences in sample size, and because richness is so subjective to that. So rarefaction are commonly depicted as curves, so each line or curve basically represents one sample or one collection. In the case of this study, this would represent one microsite. Your x-axis is just collection size, so this is number of identifiable elements or taxa. And your y-axis is just richness, number of taxa present or species. So as you can see, this sample is much higher richness than this sample based on 500 identifiable specimens. Ideally, what you want to see is when you collect a sample, you actually want to see your rarefaction curve begin to kind of plateau off. This suggests that you've achieved a sufficient sample size to basically capture the richness in that system. So as you can see in this one, the curve hasn't quite started to plateau off, which would suggest this sample actually needs a larger sample size. We can compare the sample size between these two collections, but it would kind of be moot because this one could continue climbing up and actually end up to be higher richness than this sample. The other thing that rarefaction curves allow us to do is actually kind of get an idea of evenness. So if you'll notice, These 4 rarefaction curves actually climb much steeper, much faster than these 2. That suggests that the abundance distribution of taxa in these 4 collections are much more evenly distributed than they are in these 2 taxa, in these 2 samples. For the Belly River group, the first thing I did was I wanted to look at richness through time. And I used rarefaction curves to try to account for sample size and changes in evenness. For that purposes, I basically looked at how does richness change through time at 600 specimens, 600 identifiable specimens. The reason I chose 600 was I eliminated any microsites in which the curve had not started to plateau yet. I basically eliminated those because those needed larger sample size. Okay, what do we see? So let me orient you to the graph first. This left column basically represents microsites from Dinosaur Provincial Park that had greater than 600 specimens. The right column is basically microsites from 1-4 with greater than 600 specimens. The x-axis is just richness, number of taxa. Each microsite is labeled with its appropriate depositional environment. And the y-axis is basically through time. But I also did include the lithostratigraphic kind of formations in which the microsites came from. So Dinosaur Provincial Park, we've got microsites from the Oldman, the Dinosaur Park, and the Lithbridge Coal Zone. And then it's capped by the Bear Paw. In 1-4, we have the foremost, the Oldman, the Dinosaur Park, and then the Lithbridge Coal Zone, which is also part of Dinosaur Park. And I also mapped on our radiometric dates that we have for the 2 sections. I basically put the relative age of the microsites to one another based on 77 million years old, because that age was in common between the 2 taxa, and the rate of deposition between the 2 areas is different. So just to point out again, the microsites from the Lithbridge Coal Zone in 1-4 are much younger, well not much, but are about 500,000 years younger than the microsites from the Lithbridge Coal Zone in Dinosaur Park. The black bars represent the richness of each microsite at 600 specimens based on 95% confidence intervals. This basically allows us to look at changes in richness through time and which ones are statistically significantly different. So what do we see? All right, let's look at Dinosaur Provincial Park first. We basically see no change, no statistically significant change of richness from the upper Oldman through majority of the Dinosaur Park formation until we get to Lithbridge Coal Zone. And then you begin to see a drop in richness in the Lithbridge Coal Zone, which it drops the most about in the marine mudstones of the Lithbridge Coal Zone. There's a lot of variation in richness depending on which microsite you're sampling, but for the most part, all the black bars are basically overlapping, which tells us we can't see any statistically significant difference. When we compare that to the 1-4, we see a very similar pattern. Again, you see no change in richness from the top of the foremost all the way up through the Oldman until you get to the Lithbridge Coal Zone, the very upper part of the Dinosaur Park formation. And then you begin to see, in some cases, an extremely large drop in almost half, if not more, in richness. There's a lot of variation, a lot of overlap between both the non-marine sites and the transgressive regressive paralitic sites. But for the most part, estuary-dominated portions of the coastal plain have much lower diversity, or richness, than the non-marine sites. Some of the greatest variation that you see is in the Lithbridge Coal Zone of 1-4. These all come from the same depositional environment, kind of a muddy channel fill. It's a muddy channel fill, a series of muddy channel complexes, but you can basically divide them out based on their area. So AC through GB4 are in a more eastern position or channel complex versus the rest of these are more western. and the more eastern position muddy channel fill is considered to have a greater influence in greater tidal influence affecting them. So that's potentially why we see such a much lower richness. Let's see. I don't have enough hands. Okay. So we can account for richness, but richness is extremely dependent on sample size. And probably the best example to see this is, notice how some of the bars, 95% confidence intervals, are much smaller than some of the other ones. That's actually inverse to what you would think. This actually shows the reason why this bar is so much smaller is because you're actually approaching the the limit of that collection for that microsite. So again, even though we are trying to account for changes in richness using 95% confidence interval, we're still kind of hindered as a result of richness in the sample size. So to do this, we really want to look at diversity, to see how diversity changes through time. Okay, one of the most important aspects of diversity is what's called diversity partitioning. And this is the idea in which you can divide the diversity of a biological system into its component parts. It's almost always divided into 3 component parts. You have within community diversity, or what's considered local or alpha diversity. You have regional diversity, or what's also called gamma diversity. And then you have kind of between community or differences in diversity, which is also called beta. So usually the way you calculate gamma or regional diversity is just average alpha diversity or local diversity plus differences between alpha diversity, which is called beta, differences between communities. So in this example, we've got 2 landscapes, landscape A and landscape B. That's the square. In each landscape, there are 4 habitats denoted by the circles. And then in each habitat, there are a number anywhere from 1 to 4 taxa denoted by the different silhouettes. So the regional diversity between landscape A and B is the same. It's both 4. The alpha diversity between the 2 landscapes is a lot different. Alpha diversity in landscape 1 in A is 1. Alpha diversity in landscape B is 4. Therefore, that means beta diversity in landscape A is 3, while beta diversity in landscape B is 0. So what is this telling us? Why do we care? It allows us to compare the 3 diversity. It allows us to compare the distribution of the 3 diversities between the 2 landscapes. Landscape A with a factor of 3 suggests in order to account for the diversity at a regional scale compared to the local scale is you have to have basically 3 additional habitats. When you compare alpha diversity, local diversity with regional diversity for landscape B, beta is 0. That means there is no difference between local diversity and regional diversity. This is actually extremely important in terms of trying to determine the distribution of richness or diversity across the landscape and the factors affecting it. Okay, so the way I calculated diversity through time for the Belly River group was I basically grouped microsites from the same stratigraphic horizon and depositional environment together to look at trends in diversity through time. So you guys have seen this several times already, but you have relative changes in sea level in the first column, depositional environment in the second, ages based on that we have, radiometric dates for the 2 areas that we sampled, and the rock formations and their thicknesses, and outcrop exposed at both. And then what I did was I grouped microsites that occur at the same stratigraphic horizon and in the same depositional environment, and I labeled those stratigraphic levels based on their relative age to one another. So if you note, at 77 million years, we actually have 3 different stratigraphic levels that we can look at diversity for. I also divided the microsites in the Lethbridge coal zone at 1,4 into kind of west and east, because the eastern microsites in the Muddy Channel complex had much, much lower richness than the western sites. So I wanted to see what that effect was on diversity. Just like ordination analyses, you can use various different metrics to calculate diversity. I use two of the most common ones. They're called Shannon and Simpson's. In order to calculate my 95% confidence intervals to look at statistical significant changes, I basically subsampled all stratigraphic levels to 800 identifiable specimens, and I did it about 1,000 times. All right, so what do we see? So again, we have Dinosaur Provincial Park on the left, 1,4 on the right. X-axis is effective richness, so you can think of this as changes in number of taxon. And then sites are oriented relative to one another based on their age, and then I labeled what lithological unit they come from. The black bar is 95% confidence interval for that stratigraphic level for Shannon. The gray bar is for Simpson. And then the right triangle represents crevasse splays. The open circle is a sandy channel fill. The diamond is a marine mud. And that should be a different symbol. That should be the hexagonal, which is muddy channel fill. So what are the trends we see? Well, let's start with Shannon diversity first for Dinosaur Provincial Park. So we're looking at the black bars through time. As we move from the Oldman, the upper Oldman to the lower Dinosaur Park, we see a slight increase in diversity of about 2 taxa to no increase, depending on which environment we're looking at. So we're going from a crevasse splay in the upper Oldman to a sandy channel fill in Dinosaur Park. We see a slight increase of about 2 taxa. But if we just jump from a crevasse splay to a crevasse splay from the Oldman to the Dinosaur Park, there's no change in diversity. This really isn't much of a concern, because there really is only a change of 2 taxa really isn't that big. It's pretty close for the bars to be overlapping. And this is just a reflection of the crevasse splays having slightly lower evenness. But let's see what we see through the rest of the section. So as you move from up through the Dinosaur Park, we see the lower part of the Dinosaur Park, there's no change in diversity based on Shannon's. When you get to about the middle of the Dinosaur Park, there's a slight drop in diversity. It's a bigger drop than what we saw from the it's a bigger drop than the increase we saw from the Oldman to the lower Dinosaur Park. But we climb back up to about the same levels of diversity that we saw in the lower Oldman. And then once we hit the Lethbridge coal zone, we just step farther and farther out, with the lowest diversity being in the marine mudstones of the Lethbridge coal zone. Pretty similar to what we saw. Overall, the pattern is very similar to what we saw in Richness. When we compare that to Simpson's, the gray bars, we basically see the same pattern, with the exception that there is no increase from the Oldman to the Dinosaur Park. If we go over to 1,4, as we move from the upper foremost to about the middle of the Oldman, we see a jump in diversity. It's a pretty significant jump, almost double the amount of taxa. There's a big gap where we don't have any stratigraphic levels, basically any microsites from the same stratigraphic level in the same environment. But you see a slight drop in diversity as you go from the middle of the Oldman to the Dinosaur Park, lower Dinosaur Park. And then it's a further drop when we hit the muddy channel fill microsites of the Lethbridge coal zone, the western sites, which are considered less proximal on the coastal plain, less proximal position. There is still a drop, but not as much, but there's a huge drop in the tidally influenced ones. And we see the same exact pattern when we look at Simpson. There is no difference. So, diversity, relatively unchanged through majority of the Oldman and Dinosaur Park until you hit the Lethbridge coal zone, and then it drops down. There's some slight fluctuations, but not much. See a general rise in diversity up through the Oldman, slight drop at the Dinosaur Park, and then a major drop in the Lethbridge coal zone. That's just local or alpha diversity. When we compare this to regional diversity, we see basically the exact same pattern. The effective richness values are slightly different, but you see the exact same pattern both in Dinosaur Provincial Park and 1-4, using both Shannon and Simpson diversity. If we compare that to between community diversity, or beta, basically the difference between gamma and alpha, no surprise, we see basically no change in beta diversity throughout time for the Belly River group. Let me skip ahead here. Okay, so what does this tell us? What does this tell us about diversity and how it's changing through the Belly River group as a result of fluctuations in sea level? What this is telling us is that the reorganization of the coastal landscape, of the coastal plain of southern Alberta, from a river-dominated system in the Oldman and the Dinosaur Park to an estuary-dominated system in the Lethbridge Coal Zone, all occurred at basically the habitat level, local level, and did not affect their compositional differences. The rapid change in sea level at the top of the Dinosaur Park Formation did not cause a fragmentation of the landscape. If the landscape was heavily broken up due to flooding and breaking up habitats, you would expect beta diversity to change dramatically through the section. That is not the case at all, which is actually kind of surprising, but really cool, considering we're basically working with a non-marine section. We're just talking about parts of the section that are more estuary-dominated or tidally influenced versus fully non-marine or river-dominated. So, conclusions. Coastal and inland communities represent river-dominated and estuary-dominated proportions of the coastal plain are identifiable at a regional scale. This is not real surprising considering how evident they were based on previous publications. Richness, evenness, and diversity are generally lower in estuary-dominated system, which corresponds to trends you find in a modern system. So when you look at estuary environments, they almost always have a lower richness or diversity than what you find in the fully marine or the fully non-marine environments. This is because there are very few organisms that can handle sometimes daily salinity changes in estuary environments. What's really cool, though, is the relative rise of sea level caused a reorganization within community habitats, but did not fragment the landscape. Sea level was rising so quickly that you didn't see the landscape break up. All the changes in diversity just occurred within a given habitat. The effect of sea level fluctuations on terrestrial vertebrate ecosystems has received surprisingly little attention relative to the research on marine invertebrates, fisheries, or coastal wetland habitats due to rising sea level. This study represents one of the few that examine the effects of relative sea level fluctuations on terrestrial community structure of a coastal plain ecosystem at a regional scale. Partitioning diversity revealed that flooding of the coastal plain leads up to the last major rise in sea level of the Western Interior Seaway, affected the landscape by reconstructing local coastal communities represented by estuarine systems, but did not fragment the landscape. Thank you.